because I think it's useful to have this intuition, I also want to give a few notes on Fock space for fermions, on the behavior of field operators on fermion states. So, first of all, I use this notation to denote the vacuum, always, and this notation with the lowercase a to mean a creator or annihilator. And if we create state alpha on the vacuum, then I'm just going to call that alpha. And if I do something like creating beta on alpha, that just creates beta alpha, right? Where just the state you create just goes in front. Which, because this is because this was created by a chain of two creation operators, it's what I call a blade state, meaning it's a blade in the geometric algebra sense, because it's expressible as the exterior product, as the wedge product between two vector states, right? If you will, it's a bivector state. Not only is it a bivector state, it is a simple bivector state. You may know from geometric algebra that once you're in 4 or more dimensions, then you could have something like this, right? If you take x hat wedge y hat plus z hat wedge w hat, where these are the 4 orthogonal basis vectors of your 4-dimensional space, and wedge creates an area element, x, y, and then the box that it creates is x, y, directed area. Then this bivector cannot be is not simple. It's a sum of 2 bivectors. So here's a simple bivector. Here's another simple one. It's a sum of 2 simple bivectors. So it is itself a bivector, but it is not a simple bivector because it cannot be expressed, regardless of your choices of A and B. It cannot be expressed as a wedge product of A and B, right? So similarly, there are some quantum states that cannot be expressed as a product of that cannot be expressed with one chain of creators, or as a wedge product of states, and that's important because those states, which can be like here's an example. So here, if I did a state like this, alpha, beta, equals gamma, delta, right? Using the notation that, gamma delta is, of course, just what you get if you create gamma and delta on the vacuum in that order. This is a bivector state, right? It's a 2-particle state. It's normalized correctly, but it is not simple. It cannot be expressed as a Slater determinant, which is equivalent to saying there do not exist vector states phi 1 and phi 2, such that you can do this. There may exist a more general, there does exist a state, that this is it, right? Like this state exists, you just can't express it as a wedge product. It's you need a sum of 2 wedge products, right? Which, which this delta wedge, this is whatever wedge delta is. Now, one thing, just a quick refresher, in case you don't remember, the wedge product of is anti-symmetric. So this is always true, regardless of what y and x are. They could be, the hats in this case mean unit vectors because I'm breaking into geometric algebra briefly. But I should write it more generally. For vectors A, wedge B, it's the case that this thing is always anti-symmetric with respect to vectors. It might not, if you have a vector and a bivector, their wedge product could be symmetric. In fact, it will be. If it's a vector and a bivector, that can be shown. But anyway, so therefore we use this notation. We say we're going to skip all the wedges, you know, and if I say that if I reorder the terms within a ket, then clearly I'm, you know, reordering in this sense, so a negative sign appears. Okay, great. So, the thing I actually want to go over then is so real quick, just to go over that again. You've probably heard of a Slater determinant, and you may know that not all n body states, not all multiparticle states, are expressible as one single Slater determinant. States like this are, right, blade states, because a blade is a simple multivector, right, and a state is a vector or multivector in the case of a you know, n body state. But if you have so something like this, something like alpha, beta, delta, where those are all one particle states. This is a blade state, right? Whereas again, something like 1 over root 2, you know, alpha, beta plus delta, gamma. That's not a blade state. That is not expressible as an exterior product. Okay. The reason I'm telling you this is so that we can establish what the creation and annihilation field operators do to some simple blade states. So that we'll start with the most simple case. If you have a one particle state alpha, normalized one particle state alpha, what does the annihilation operator do to alpha? To figure this out, part of what we can do is, and I'm going to abbreviate the annihilation operator psi of x as just x, and I'm going to abbreviate the creation operator that appears here as alpha, right? Alpha dagger, because, you know, it creates the state alpha on the vacuum tube. Okay, you with me so far? Anyway, so because the anticommutator of x and alpha dagger is the projection of the state x onto the state alpha, we can take advantage of this, right? This means that x alpha dagger equals this projection minus alpha dagger x. So here I'll write that. And of course the vacuum is still here. Now remember, x is just standing in for this this field annihilator. So x is annihilating the vacuum, right? So clearly this business is going to go to 0, but this business is not, and we end up with x on alpha times the vacuum, which, using the usual convention for wave functions, is just alpha of x, where, you know, that symbolizes the way that alpha looks in the coordinate basis. Alpha of x times the vacuum. So there you go, there's our conclusion. The conclusion is that if you annihilate, you know, if you remove a particle at a particular spot from a state where that particle could be in a bunch of different spots from one particle state, you end up with the function alpha of x. This is a scalar function of scalar parameter x times the vacuum state. So that's sort of the first result that's interesting today. This will help you in computing certain things, just to know this shortcut, right? Because you know, it's sort of an interesting question. Like if the particle x is if the particle is in a superposition of two different places and you annihilate it just here, what happens to the whole state overall? And this is what happens. An entire particle is removed. We've gone from a one particle state to a zero particle state, but we scaled it by the degree to which there was a particle there to remove, if that makes sense. Next up, let's remove a particle from a bivector state, from a simple bivector state. Okay, Great. Let's do it. Annihilate at x on alpha beta. Okay, and alpha beta is a simple bivector state constructed, using two creation operators if you like. Anyway, so we're going to do a similar procedure to last time. We're going to unpack the creator of alpha, which I shouldn't have skipped notation quite so fast earlier. Sorry. On beta, right? And we're going to use the commutator relation again. Clearly, this is going to be x on alpha minus. Okay, I'm going to start getting lazy again. Minus alpha dagger. Dagger x, and again, x is just shorthand for annihilate at x. Okay, it's all this on beta, which means we can, I'll do a carriage return. That means you got alpha of x beta minus, minus alpha dagger x beta, and we already know, I'm going to put parentheses here to clarify it. We already know what x on beta does, right? X is the annihilator, and we know that the annihilator on a one particle state does this. So this is going to be alpha of x beta minus, create alpha times, okay, we know what this is. It's going to give us beta of x times the vacuum. Beta of x times the vacuum. And, this is an operator, this is a scalar, so it can go right through. And when create alpha acts on the vacuum, it's going to, create the state alpha. And so what we end up with is this expression, which hasn't changed in a few steps, alpha of x times beta, minus beta of x, scalar, so moving it to the back. And then when create alpha acts on the vacuum becomes the single vector state alpha. And so in conclusion, if you annihilate a single particle from a bivector state, what you end up with is a sort of superposition that's anti-symmetrized in a certain sense, right? Between the two vectors that comprise that simple bivector state. Alpha of x times beta, beta of x times alpha. You can probably see the pattern here. If you may guess, right? You may have already guessed if I annihilate a single particle on a trivector state, a simple trivector state that I'll call alpha, beta, gamma. That is similarly anti-symmetrized. You end up with, and this is sort of interesting, alpha of x, you get alpha of x, beta gamma, minus beta of x, alpha gamma, plus gamma of x, plus gamma of x, alpha beta. And so there's your trivector action. Some exercises for the reader will be, what happens if I take a second annihilator? If I do something like annihilate x, annihilate y on a bivector state or a trivector state. Hell, what happens if I do it on a one particle state? That's an important question. Another one is, what if I act on a non-simple state? Like this one. Why don't I try applying a annihilator to that? And you can actually see very clearly what happens, right? Obviously, since this is a superposition of those two, and it's a linear operator, it's going to act on each part individually. You're going to end up with, like in this case, alpha x beta minus beta x alpha plus delta x gamma minus gamma x delta, and so on. So that's there's certain derivations where, well, many derivations where simply having this intuition will help you a little bit. So don't remember, you can manipulate operators even if you don't. It doesn't have to be inside of an expectation value for you to be able to move these operators around, right? You can directly say, okay, I know what this annihilator is going to do to this state in certain circumstances, and that can help you understand things a little better. So, yeah, thanks for watching. All right, bye.